Alright guys, so we're going to go ahead and get started with our lesson for today. We are going to be talking about oceanography. Oceanography is a study of what? So when I say we are learning about oceanography today, what is oceanography the study of? Is it the study of oceans? Is it the study of space? Or is it the study of plants? Oceanography is the study of the ocean. So oceanography is the study of oceans. So plants can be involved in oceanography. So can a lot of different things. There are four main branches of oceanography. So there's geological oceanography, there is physical oceanography, there is chemical oceanography, and there is biological oceanography. I'm going to get into the first three. I'm not going to be teaching you guys about biological oceanography because honestly that's kind of what we've been doing so far by teaching you about all these living things in the ocean. So I don't think we need to go over that again. But let's go ahead and start off with geological oceanography first. So geology is just kind of the study of landforms and rocks and everything, continents, volcanoes, tectonic plates. So we're going to go ahead and start first off with Pangea, and I'm going to grab my globe really quickly. Alright guys, so we're going to be looking a lot at this globe today so I can help you guys kind of see things. It's not the best globe for what we're doing. I didn't really have those globes that many of your teachers would have. But Pangea is actually a supercontinent. So guys, a continent is this, like North America, South America, those are all continents, right? And Pangea is the idea that all of our continents were actually one big supercontinent. So at one point in time, researchers and scientists think that all of this is stuck together. And if you guys look at the way these continents are shaped, it kind of makes sense. Look at South America and look at Africa. They could kind of be puzzle pieces. So the idea is that 600 million years ago, we had what we call Pangea, and it was a supercontinent. And over time, it broke up into what we have now. Then what we have, we call Continental Drift. So the idea of Continental Drift is that our crust on Earth is slowly moving on top of a liquid core. So some of you, maybe you older students have learned about this with tectonic plates. And it goes along with the theory that our continents have slowly moved over time, and they are currently still moving. Now, tectonic plates, I'm not going to get into too much, but a tectonic plate is just think about these plates of Earth's crust kind of moving on this liquidy lava layer all around, and there's a bunch of tectonic plates. There are 7 major plates, so the 7 major plates are kind of just the continents, actually. So think about your continents, and those are the plates. And they're constantly moving and creating mountains and trenches. So we have what we call a divergent boundary. So everyone go ahead and put your hands up. So a divergent boundary is when the plates move away from each other. So just go ahead. Each hand is a different tectonic plate. Move them away. So that is a divergent boundary. And when you have these plates moving away, you can have earthquakes, you can have volcanoes, and it creates new crust, especially in the ocean. So when that happens, when it spreads apart like that, you'll actually have lava come out into the ocean, and it'll quickly cool off and create new ground. So you're actually getting more land or more crust as that happens. All right, now everyone do this. All right, and put your hands together. So now we have a convergent boundary where your plates come together. Now when your plates come together, all right, they create either mountain ranges or trenches. So they can come together and press up to make a mountain, or they can come together and press down to make a deep, deep trench. And we're going to be learning about a trench today, and Miss Alex next Friday is going to be talking all about the deep ocean, so she's really going to be getting into those trenches then. All right, the next one, everyone put your hands back up and do this. This is what we call a transform boundary. It's when the plates slide against each other. This is a really, really big one responsible for earthquakes. So earthquakes largely are caused by these transform boundaries. They can create faults and canyons. We have a lot of underwater canyons as well. and will also crumble the crust. Now, for those of you that live kind of in the Pacific Ocean, so on the coast here, on the west coast of America, all right, all the way up, and then on the east coast of Asia, right here, you live in what we call the Ring of Fire. So it goes all the way kind of around the Pacific Ocean there. And the Ring of Fire is just where the tectonic plates are really interacting, and that's where you have a lot more earthquakes and volcanoes. So this area here is called the Ring of Fire because the tectonic plates in this area create a lot more earthquakes and volcanic eruptions. We do still have volcanoes in other parts of the world. We still have earthquakes, but they're very, very common in this area. If you guys live in those areas, you probably understand that already. All right, so let's move on to physical oceanography. So physical oceanography, we're talking waves, tides, currents, and the ocean zones. What controls the tides? All right, so what controls the tides? Is it the moon and the sun, or is it Mars and Venus? Which one controls the tides? You guys mostly got this one too. That's awesome. So the moon and the sun control the tides. So the gravitational pull of the moon and the sun make the water in the oceans bulge, so get a little bit larger, causing a change between high and low tide. So it's the moon and the sun that really depends on the tides. Especially like during full moons, you have really extreme tide changes. So we actually just had a full moon, and down here it's got flooded because of the high tides. So down here, if we have a really high tide, our storm drains that lead to the ocean. If you don't know what a storm drain is, it's those grates in the ground, usually by the sidewalk, for when it rains, everything kind of goes in there. Down here, anything that goes in those drains goes directly into the ocean, and that means that during a high tide, the water will actually go back up into that storm drain and flood the streets. So last week, we actually had a lot of street flooding with ocean water, so the ocean was kind of coming back up. And sometimes people actually find fish in their yards from that event that happens. So when we have a full moon, we have really extreme tide changes here, especially. So your tides are daily. So we'll have high tides twice a day, low tides twice a day usually. All right, so now let's talk about waves. If you have this work, go ahead and pull it out. I'm going to work on this with you guys a little bit. Okay, so I'm going to go ahead and post another poll question for you. What do you think the top of the wave? So I made a obviously very simple wave diagram, but what do you think the top of the wave is? What is the top called? Is it the trough or the crest? So the crest is actually the top of the wave. So if you have this worksheet, you can go ahead and write crest right there. All right, so the trough is going to be the bottom. So the bottom here is the trough. So that would be the trough. If you think about it, think of what I believe horses and maybe cattle and other livestock, they drink and eat out of a trough, and it's like this big bucket that's usually on the ground. So think of it that way. Lower is the trough, the crest is up higher. Okay, so I'll go ahead and write trough. All right, guys, so waves is the up and down motion of the ocean, and it's caused by winds traveling across the surface of the water and transferring that energy. Remember, guys, energy can never be created nor destroyed, it's just transferred. Now, the energy creates friction. So friction, think about when you're rolling across, maybe on a skateboard on a rough road, eventually you're going to stop moving, right? That's friction. So the energy creates friction, which forms these waves that we have in the ocean. All right, so we've got the crest and the trough. Now we have to figure out these 4 boxes here. So the wave height, go ahead and make a guess as to what you think the wave height's going to be. All right, I'll give you a few seconds to guess that. All right, so the wave height is going to be from the crest to the trough. So your wave height is going to be right here. That is your wave height from crest to trough, right there, okay? So that's your wave height. So go ahead and write wave height there. Alrighty, so now let's think about wavelength. So what do you think the wavelength is going to be? Give it a guess. So the wavelength is going to be right here from crest to crest. That is going to be your wavelength. So guys, your wavelength is crest to crest. Your wave height is crest to trough. All right, guys, and I have these two on the bottom. I'll let you guys kind of give that a guess later on and check your answers on our blog post. I'm going to go ahead and explain to you the 4 main types of waves that we have. If you guys like to surf or go to the beach, this might be a little interesting for you. So there are 4 main types of waves. We have spilling wave. So the spilling wave is produced when the ocean floor has a very gentle slope and the crest of the wave, so the top of the wave, spills slowly forward until it is all white water. When I say white water, think about a wave and you see that white part, that's the white water. So spilling waves go up a gentle slope and they just kind of spill forward. You have your plunging waves. So your plunging waves is when an incoming swell hits a steep part of the ocean. The wave's crest curls over and explodes under the trough and you have a crashing sound. A lot of surfers love the plunging waves. Your surging waves are long swells that arrive at coastlines with steep beaches. The waves don't always break like you would imagine, and they can be deadly. So surging waves are with a lot more floods, kind of deals like that. So your surging waves are the more dangerous ones in terms of when you're on land. Then you have a collapsing wave. So a collapsing wave is a combination between a surging and a plunging wave, and it never breaks and it ends up with a bunch of just white water. So it just kind of falls on itself. So it collapses. All right, so again, I mentioned how waves are formed is from the friction of the wind. So it actually is part of what we call the Coriolis Effect. So the Coriolis Effect makes things traveling in different distances appear to be moving at a curve rather than a straight line. So an example that I saw is, say you're in Texas and you throw, so I'll actually show you, say you're right here in Texas, it's kind of hard to see, and you throw a paper plane, you would imagine it would go straight up right here into Nebraska. But because our Earth is constantly spinning, and guys, certain parts of the Earth are spinning faster than others because we're a sphere, we're a circle. So up here on the North Pole isn't spinning as fast as we are on this line here, which I'll ask you in a second. So if you throw a paper airplane from Texas to Nebraska, it's not going to end up there because Earth is constantly spinning. It's actually going to deflect and move more towards the East Coast. So if you throw a paper airplane straight from Texas, hypothetically, it would actually end up on the East Coast and it would not end up going straight. The line that goes through the middle of the planet, so this line right here, what is it called? Is it the Tropic of Cancer? Is it the Tropic of Capricorn? Or is it the equator? So again, guys, the idea of Coriolis Effect is that the Earth is constantly spinning, but things located here near this line are spinning faster than those that are closer to the poles. Okay, so closer here, you're moving faster. You are up here or down here. That's the idea of the Coriolis Effect. It's the idea that the winds are not moving straight. They are always moving at a curve to some angle. All right, guys, so most of you got it. The answer is the equator. So the equator is right here. It's that center line in the middle of the planet. If you are closer to the equator, you are spinning faster than you are if you're towards the poles. Guys, if you threw that airplane straight ahead, it's not going to go straight, it's going to curve. So guys, we have what we call gyres and currents, and that's the idea that our water doesn't move in a straight line either. They actually spin and move in circles. So you guys know that a toilet, the water moves into the center. If you guys ran around in a pool or a hot tub a lot, all that water would slowly start moving in a circle. It's really fun. Then it'll just carry you around. That's a gyre. So it's circular moving parts of the water. And in every major ocean, we actually have what we call gyres. All right, so I'll give you guys another question. This one's should be an easy one. How many continents are there? So how many continents, major continents, do we have? Do we have 5 or 7? How many major continents do we have? While you guys are guessing that, go ahead and pull this worksheet out here, okay? All right, guys, so while you're guessing, I'm going to explain again the globe a little bit more to you guys. So up here on top of the equator is the northern hemisphere. Down here is the southern hemisphere. So when I said you mostly find olive ridleys in the southern hemisphere, this is what I was talking about, all right, below the equator. Again, this is the northern, this is the southern hemisphere. All right, you guys are correct. There are 7 continents. So there are 7 major continents. So go ahead and on this worksheet, if you have it, go ahead, for those younger, I want you guys to go ahead, well, all of you, but you guys to go ahead and label the continents. So the way I have this worksheet is that for the younger ones, I want you to be able to identify the continents and to be able to identify the oceans. As you go up in levels, I want you guys to be able to label the currents, and I'll talk about the currents soon. So go ahead and label your continents if you can. So again, guys, these winds are moving the water to go in a circular pattern. So in the northern hemisphere, our water moves clockwise. So it moves like this. So here is, let me see if I can make this easy for you to see. There we go. Our water moves like this. One big clockwise rotation. So your water goes up the East Coast, out to Europe, down Africa, then back around. So your gyre in the North Atlantic Ocean moves in a clockwise circle. Same here in the Pacific. It moves in a big clockwise pattern there, just like that, okay? So in the northern hemisphere, your water moves in a clockwise spiral. In the southern hemisphere, you can probably already guess it moves counterclockwise. So here in the southern hemisphere, it'll go up South America, across to Australia, then back down. So counterclockwise in the southern hemisphere, clockwise in the northern hemisphere. So right here, here's this other space to show you. Goes up Africa, down South America, just like that, okay? So if you want to go ahead, and now after you've labeled your continents, all right, or if you don't have the worksheet, just name the 7 major continents out loud for me. Then name the major oceans, okay? So there are a lot of different oceans, but I want you just to name the major oceans. So where is the Atlantic Ocean? Where is the Pacific Ocean? The Arctic Ocean, the Indian Ocean. So go ahead and label your oceans there. All right. And once you do that, I want you to be able to start labeling the currents. So again, I said that the currents in the northern hemisphere, so we'll kind of make a line right here. I'll draw a line for you all. It's not exactly where the equator is, but you know, we're just kind of approximating it. So the northern hemisphere is up here. So again, guys, the water in the northern hemisphere goes clockwise. So just like this, like that. And in the southern hemisphere, it's counterclockwise. So like this, okay? Now, the water doesn't just move in a circular pattern. It's not just the same water. What happens is the water will actually change temperatures as it moves through that gyre system. So for those that are more of a higher age level, higher grade level, what I want you guys to do is to try to label the temperature of the water that you think with crayons. So red or blue crayons here. So I'll do one example for you guys. So in the northern Atlantic Ocean, what happens is the warm water actually travels up the east coast of America, and then it begins to cool off towards Greenland, and then we get cold water that comes back down across the coast of Africa, and then it warms up again. So this is exactly what it looks like here. The warm water goes up the east coast of America, of North America, right there, up the east coast to Greenland, where it starts to cool off. Then it cools off, brings cold water down, and then it warms back up down here. All right, so that's an example. I'll let you guys kind of do the rest of what you think would happen. Okay, down here, I will give you a hint. Down here, you'll have just cold blue lines going across. So I'll let you guys kind of make your guesses on what you think happens, and then you can actually check your answers on our blog post. I have all the answers up there. All right, guys, so I do want to tell you a little story about how we learned about our currents. So it's called The Story of the Rubber Ducks. I did post a really nice video of it in our blog that you guys can check out later. But pretty much a bunch of rubber ducks like the ones that you think about in bathtubs, a bunch of rubber ducks actually told us and taught us how the ocean currents work. So back in 1992, there was a big ship traveling from Washington, the state of Washington, to China. And there was a big storm that hit, and these big containers became unstable and spilled 29,000 rubber duckies into the ocean. So in 1992, almost 30,000 rubber ducks fell into the ocean. Obviously, that's not good because that is littering, but you know, scientists were able to make lemonade out of lemons, and we got to learn. So after that, rubber duckies started popping up all over the world. They were popping up in Scotland, they were popping up in Africa, and we were in Australia, in all these different places. There's still rubber ducks popping up to this day. And the idea is that we are learning about how these ducks moved through the currents, and actually taught us a lot about the gyres and everything that's going on in the ocean. So check out that video that I posted on our blog. It's very cool. It's very cool to learn about these rubber duckies and how they help scientists learn more about our oceans. And another thing about gyres, guys, probably a lot of you have heard of the Great Pacific Garbage Patch. The Great Pacific Garbage Patch is the one that is in the northern Pacific Ocean here. And the idea is that because the water is moving in a circular form, all the trash that's in the ocean kind of gathers into one space and creates these big floating patches of trash. And it's present in all the gyres. We actually have one in the Gulf of Mexico down here, but the Great Pacific Garbage Patch in the Northern Pacific is the biggest. And Miss Alex is going to teach you more about that on Friday with her water quality lesson. It's actually very interesting. There's a lot of cool videos about it. All right, so guys, now we're going to learn about ocean zones. So that's this worksheet here. Again, if you don't have it, that's totally fine. Just listen along. It's totally okay. So ocean zones. Pretty much there are quite a few different zones in the ocean. I'm going to just tell you about them, and then Miss Alex is actually going to be teaching you guys next Friday about the deep ocean. So she's going to be teaching you guys more about what happens. Before I just go into ocean zones, I'm going to ask another question. Is there sunlight in all parts of the ocean? Yes or no? So there is not sunlight in all parts of the ocean. It's actually very dark in most of the ocean. All right. Before I tell you about the ocean zones, I want to give you guys another little poll question because this is cool. How deep is the deepest part of the ocean? What do you think? How deep is the deepest part of the ocean that we know about, at least? There could be a deeper part, but this is what we know is the deepest right now. Do you think it's 36,000 feet or 12,000 feet? All right, most of you are getting this one too. That's awesome. So the deepest part of the ocean is 36,000 feet. That equals 10,972 meters. So that is the deepest part of the ocean. And Miss Alex is going to be teaching you guys about that next Friday. It's super cool. The average depth of the ocean is 12,000 feet or 3,657 meters. So the average ocean depth, so how deep the ocean is on average, is about 12,000 feet or 3,657 meters. A few other really fun facts that I found really quickly. So the deepest free dive. So free diving is when you dive in the ocean and all you have is a mask, snorkel, and fins. You don't have scuba gear. You're just holding your breath the entire time. The deepest free dive, so again, holding their own breath, was 214 meters deep, which is equal to 702 feet. So that's the deepest free dive. So someone went 702 feet deep on breath of air. It's pretty crazy. Okay. The deepest scuba dive. So that's when you're actually breathing air you have attached to you. The deepest scuba dive was 302 meters, which is equal to 1,090 feet. That's pretty deep too. It's very, very deep. For those that have ever scuba dove before, actually, as you go deeper into the ocean, it gets more and more pressure on your body, so it's actually very crazy. Deepest that a human has gone in a submarine. So a submarine is kind of like this little vehicle that go underwater and can withstand really high pressures. The deepest a submarine has gone with a human in underwater was 35,756 feet, which is equal to 10,898 meters. So the deepest a human has ever gone in a submarine is over 35,000 feet deep. That's almost to the bottom of what we know of as the ocean. And the man that was actually in that was James Cameron. He helped make the Titanic. So that's pretty cool. Again, Miss Alex will teach you guys about that next Friday. So definitely want to listen to that lesson. All right, so let's talk ocean zones. We'll go back to this. All right, so when we talk about ocean zones, we have 3 on the top. So think about as you from looking on land out to the ocean, there are 3 zones that go this way. So your intertidal zone, so people know of as tide pools. Your intertidal zone are areas that are exposed to low tides or exposed to air during low tides. So your intertidal zone is very, very, very shallow water. We have the neritic zone, so go ahead and say neritic out loud. The neritic zone is where you will find light in the ocean still, so it's more shallow. So I'll give you guys a hint. Your neritic zone is going to be right here, okay? Because that is where you're still going to get sunlight, right in this box. So your intertidal here, your neritic here, and your oceanic zone is going to be where you have open water, it's deeper water. So your oceanic zone is where water is deeper than 200 meters or 650 feet. So those are your zones that way. Again, you've got intertidal, neritic, oceanic here. So now let's talk about as we go down in the water. So your sunlight zone is going to be the top portion of your ocean. The sunlight zone is the upper 200 meters or 650 feet of water where you can have sunlight going into the water. So guys, that means that right here is your sunlight zone. So from here on out, all these zones here do not receive sunlight. So that first zone there is going to be your sunlight zone. Now the next zone you have is called the twilight zone. The twilight zone is going to be about 200 meters and goes all the way down to 1,000 meters. So it's going to be your next box. So your twilight zone is between 200 to 1,000 meters. In your twilight zone, there is very little light. You mostly have bioluminescence. Bioluminescence is animals that can kind of make their own light and they kind of glow. It's very cool. You guys might have seen pictures of bioluminescence on beaches. Sometimes when the waves crash, it will glow a green or a blue. That's bioluminescence. Think of like a glow stick almost. So your twilight zone is very important for the transport of carbon, transport of carbon, and they also help regulate Earth's climate. So the twilight zone is very important for our ocean. The next zone we have is the midnight zone. The midnight zone is very, very dark, very cold, and has very little life. So there's no light here. There's very little life. The midnight zone is between 1,000 meters and 3,000 meters. So right here is that midnight zone. Next, you have your abyssal zone. So think of the abyss, right? Very, very deep, very scary, very spooky. Your abyssal zone here is between 3,000 to 6,000 meters. All right, so that's pretty deep. So right here is your abyssal zone. It's very, very dark. There's no light. Okay. Down here is where you have your trenches. So think about what I was telling you where that submarine went. That submarine went into a trench like this. Okay. Your trenches are going to be located in the Hadal zone. Okay. That is water deeper than 6,000 meters. This is where you have your underwater trenches and your underwater canyons. So your deepest part of the ocean is the Hadal zone. Okay. All right, guys, so again, you can, now that I kind of gave you the information, you guys can go ahead and work on it. It's pretty easy. You can also begin to color it based on kind of what you think. So it would be more of a lighter blue here, fade into a deep, deep purple black down there if you want to color it. All right, guys, so let's move on to our last topic, which is chemical oceanography. I'll put my, if I can, I don't know if I can actually post it. It's not letting me do that. So we're going to talk about first why the ocean is salty. I was going to have a poll question, but it's not working out on my end. So I'll just go ahead and tell you why the ocean is salty. So the ocean is salty because of rocks on land. So again, guys, water is H2O. Okay, that's what water is. And the salt comes from when it rains. So when it rains on land, the rain is slightly acidic due to the carbon dioxide that we've put in the environment. So the rain is slightly acidic, so it'll actually wear and weather a lot of those rocks. The rain will erode the rocks and put salt into the ocean. So the ocean is salty because the rain rains on rocks, the rocks break up over time and put salt into the ocean. So that's the really quick version as to why the ocean are salty. So the most common ions found in salt water is actually chloride and sodium. If you guys know what table salt is, that's sodium chloride. So that's another little fun fact for you. All right, guys, so let's briefly talk about carbon dioxide and climate change. I've mentioned it a few times already. So guys, carbon dioxide, go ahead and write in the comments, what do you think produces carbon dioxide? Go ahead and write in the comments, what creates carbon dioxide, or you've probably heard the term CO2. What do humans do that creates CO2? It's by burning fossil fuels, so driving cars, flying planes, factories. All that creates carbon dioxide. That carbon dioxide enters the air or the atmosphere. Now, guys, I'm sure you've poured something into a cup or a bowl. If you don't stop pouring, that's going to overflow, right? So our atmosphere, our air, is kind of like a bowl. It can handle so much carbon dioxide, but too much and it will overflow. When the atmosphere overflows with carbon dioxide, that carbon dioxide goes into the oceans. The ocean will absorb it. More than 30% of carbon dioxide that enters the air goes into our oceans. And our oceans will store it. It goes into that twilight zone. Our marine plants will convert it into oxygen as best as it can. However, when that CO2 or that carbon dioxide enters the ocean, a bad thing can happen. So we just had Easter. Maybe a lot of you dyed your Easter eggs. And when you dye the Easter eggs different colors, you have usually vinegar and little color tablets. So think about what happened when you put those little color tablets in with the vinegar. What happens is those tablets dissolve slowly. And that's because vinegar is very acidic. Something that's acidic, lemon juice. Think sour. Think that your stomach would hurt if you consumed a lot of lemon juice, right? So when carbon dioxide enters the ocean, it mixes with the H2O and creates carbonic acid, which means that the ocean gets very acidic. So think about the ocean turning more vinegar-like or more lemon juice-like, okay? When that happens, our shelled animals like our conch shells, our crabs, our lobsters, our sea urchins, all those will actually start to weaken and dissolve, just like the little color tablet when you're dyeing your Easter eggs. So when the ocean gets more acidic, your animals, especially the ones at the bottom of the food chain that are very important, will begin to get weaker and weaker. They're also finding that your seafood, so your fish, will actually get smaller and smaller. So your seafood will get smaller, the bottom of the food chain will start to break apart. And guys, it's also bad for corals. So I told you a while ago that corals have a limestone skeleton. That limestone will dissolve. So that's another very big issue. All right, guys, to wrap it up with our oceanography lesson, I do just want to point out that pollution is a big problem. I mentioned the Great Pacific Garbage Patch. You'll learn more about that on Friday. 8.8 million tons of plastic end up in the ocean per year. We've got fertilizers, pesticides, nutrients that can create dead zones, so that's areas where nothing can survive. We've got oil spills from offshore rigs that leak or have big catastrophic events. We actually had an oil spill in the Gulf of Mexico not too long ago. Poor sewage treatment facilities. So guys, our sewage, every time you flush a toilet, it all goes somewhere. In a lot of areas, sewage treatment is not the best, and it ends up leaking into the nearshore areas, into the water. We also have red tide events where you have a lot of nutrients, a lot of bacteria in water that help really make these algal blooms very, very strong.